Hey, excuse me. Welcome. Everyone ready to get started? Okay. So I've got your exams to pass back. We'll do that at the end of the second section that we'll do because we've got two sections to cover getting into chapter 4. We're going to talk about how it relates to what we've already been doing, make those connections. And then when you get your test backs, and again, there was a variety of results. So if you did miss any questions, you'll have the opportunity to do test corrections. And I'll explain that a little bit more depth, but basically anything you missed, you'll list that on a piece of paper. The first thing you'll do is you'll give me your answer and why you got it wrong. And we'll talk about a few reasons why you might have gotten it wrong. Then you'll put the correct answer. And again, you can get help on this as well, so I want you to do it. But the important part is the explanation of why you see that answer as being correct now. So an explanation of why the old answer, you see that it's wrong, and the new answer that you see why it's correct. Okay, and then you can get half the points back. So a 7 can become a 9. A 9 can become a 10. You get however many. It was out of 11 questions. So we'll do that in the second half. And the second half is a little bit shorter, so this probably will take about 40 minutes for the first half as we get into things. We'll build on that in the second after a little break, and then there'll still be time to, if you want to start working on test corrections or anything else. The other things I noticed, usually if I see people haven't been doing homework, they don't do so well on the test, but it was a mixed bag. Some people who didn't do homework did okay on the test. Maybe because they were doing the test review and they were learning it that way, that's fine. But the homework and the homework quizzes together are 30% of the grade. So it does make a difference if you haven't gone through the homework. And it's still valuable to go back and do them if you haven't. So I leave them open. You can still work on them. I would suggest finishing up anything from chapters 1 through 3 by the end of this next weekend, if at all possible, so then you can focus on the new part. The worst thing to do is get behind, and then you're always trying to caught up, and you never get caught up, and then because the exams are the biggest part of the grade. Okay, so you want to be able to focus on the new stuff as well as catching up. I don't put a due date, but again, it's just better if you can focus some time, whatever was from chapters 1 to 3, get it as caught up as you can, and then move forward. And then do well on chapters 1 through 6. So I'm going to see. So yes, today here's our schedule. We took the exam last Thursday. We're going to look at 4.1 and 4.2 on probability, and then we'll finish up probability this Thursday as well. Let's go here. Show you what the resources we have in chapter 4. There we go. Probability. Okay, so you'll see there is a textbook in here already. That's why I thought there was textbooks in the other ones. All these chapters have the textbook in there. I do encourage you to at least scan over them, the material that's in these chapters. We do talk about in class from the PowerPoint. So you'll see we'll talk about empirical probability today. But this gives also some additional examples and some additional explanations. Not that you have to necessarily read it all, but at least scan over it. You start to see, you'll see this formula in the presentation and the PowerPoints. But it's always good to, again, take another look and see some examples, even if it's just a quick overview. And then we'll actually get into theoretical probability as well. And so there's things in here. And again, a different, it's a multiple ways of learning, right? Because we're listening and maybe seeing, they're your reading. There's, their brain works differently when it's in those different academic modes. So it's there. I encourage you to take a look at it from time to time, take a read. We're going to go into slide deck 4.1, and you'll see there's different ones for each of them. 4 is on topics, so it's going to be integrated more as a review because it's an application. We're going to go into the basics. Let's see, we'll go here, and we'll go into our slideshow. Okay, so if I mention the word probability, what does that mean to you? Probability. Okay, a random percentage of what? A chance of something happening or a chance of something not happening. We could talk about both of those, right? Very good. So we're not talking about certainty. We're just talking about the possibility of something happening and then measuring them. Again, we'll see with percentages. Exactly. So probability is a chance of something happening. One of the things I want to focus on is when we're talking about probabilities, there has to be this aspect of randomness. It has to be random. If it's part of a design, probability doesn't really enter in so much, right? I mean, it could. I make a plan to go do my homework, and it might happen or might not. But if I make a plan, it's much more likely than if I just randomly, I'll throw a die and then see if I do homework tonight or not. And if I get a 5, I'll do homework. If I get any other number, I don't do the homework. That's probability, right? So that randomness part of it. So the definition of random, because we use random in many different ways. We could just say some random person coming along. It's not necessarily random. It's the next person. It's just random because we didn't know them, right? But randomness means that it lacks a definite plan, because if you make that definite plan, it's no longer random, right? You're going to go do something. You bought the air ticket to go see your grandparents over Thanksgiving. You're going because you paid the money, right? It's not going to be random. Random things could happen along the way, but you've got your definite plan. You've got something with purpose, and you've got something that's a pattern. We're going to talk in probability about things like card games. How many of you have played a card game at least once in your life? Okay. And how many of you have opened up a new deck of playing cards? Would you call, when you open them up the first time, would you call that random? Have you ever looked at what a new deck of playing cards is? It's organized, isn't it? It's 2, 3, 4, 5, 6. It's by suits. It's not random. So you don't start playing a game with a new deck of cards and not do it. You randomize them, right? You shuffle. And even on an old deck of cards, you don't just pick them up and start playing. You randomize them first to make the game really probabilistic, and it's random. I mean, that's how probably a lot of magicians do their magic. Is it's not random. It's just they make us think it is. Okay. So randomization is no pattern, and things happen by chance. Okay, what I want to do, this is a slide back from chapter 2. We talked about building a frequency table, and while we didn't call it probability, I'm going to show you we've actually already done all the mathematics for probability that we need. It's already been done. And so I'm going to go back and review from chapter 2, and we're going to see. And then now we're going to call it probability. And you say, oh, okay, I already know how to do this, right? Hopefully. So this is sort of in the middle of the presentation, but what I want to focus on, yeah, we did have to get the classes. We had to look at the data, but let's get past that. The part that's probability is once we had the data divided into the number of classes we wanted. In this particular example was 1, 2, 3, 4, 5, 6, 7 classes. The next thing we had to do is we needed to count how many pieces of data were in each class. And that's the first step of probability, counting. How many of you feel confident about counting? 1, 2, 3, 4. Yeah, I can do that. But what we're going to see today is we're going to count really big stuff. And so we're going to come up with some systemized ways of counting even that will make it easy for us. It's not really a big deal. It's just multiplying. But we would, again, remember we would go through and say, okay, 155, I'll put one tally mark, 165, another tally mark, and then I look, oh, here's 168, another tally mark. And so I have a frequency of 3 in that class, right? So between 155 and 190, we know there's 3 pieces of data. And so we do that for all of them. We get all these frequencies. We total them all, so we know there are 30 pieces of data. And that's the beginning. Now, if I were to say that I would so the way it becomes probability is now I'm going to randomly choose one of those pieces of data. I'm going to randomly, they're in a bag, and I'm going to pull one out. What would be the probability of pulling out a number from a particular class? So just looking at the frequencies, which class do you think would have the most, would be the most likely for me to draw out? And why do you say that? He's got the most marbles in the bag, as we would say. Yes, so there would be the most, there's 7 in there, right? So that's all probability is. It's most likely to happen. What would be the least likely one to draw out? You got it. See, you're already experts. Here, I can't draw a nice line, but there we go. So, because there's only 2, that's the least amount. So that's all probability is out of 30 chances of pulling something, 7 out of 30 is bigger than 2 out of 30. That's all it is. We are going to turn it to a percent because that's a lot of times easier to judge between 1 and 100 than doing it with different denominators. Although the homework sometimes will ask you to give your answers as fractions, 7 out of 30. My preference, personally, is percentages because it's a lot easier for me to understand from one to the next. How does 7 out of 30 relate to 5 out of 12? I can't even think of it right now. But if you give me the percentages, I can compare them directly. So that's why we go to percentages. So then the part that becomes the real probability part is when we turn it into a relative frequency. So how did we take the frequency of 3? What was the math we did to turn it to a relative frequency? We took 3 divided, right? By what? The total. 3 divided by 30. In fact, that's what you're going to do to each of these. You just divide them by the total number of frequencies. And that gives us a relative frequency or a percentage. So 3 divided by 30, plug in your calculator, you'll get 0.10. Turn it to a percentage. You either multiply by 100, or which would cause the decimal to move over 2 places, or call it 10%. Again, I like to use the 10% because it's easier to work with for me. You can use the decimals, 0.10. It's the same thing, but again, percentages are easier than decimals for me. You can also use the fraction, but a lot of times they'll take this fraction, they'll put it as a reduced fraction, which is 1 out of 10, and you lose information. I mean, 1/10 is, you don't get the fact that there's 3 out of 30, you only get that there's 1 out of 10. So it is reduced, but I don't really like to use fractions if I don't have to anyway, for most part. So a percent would give us 10%. And I can picture what 10% is like. Here's 100, here's 10%. So it's a little bit. We would do that for each of these, right? Even this big one, we take 7 divided by 30. I did this earlier. I think it's like 26%, 23%. Don't remember exactly, but it's bigger than 10%. We get all our percentages. If we take our relative frequencies as decimals and we add them all together, what are we always going to get? 1, right? The decimals will all add together to 1 because that means we have, as a percentage, 100%. We don't get 100%, that means we're missing something. If we get a more than 100%, it means we probably counted something twice, right? So, and that's probability. All we're doing now so we did this with frequencies just to get the percentages of each. We're turning it into probability by adding the randomness that now we're going to randomly choose something, a piece of data, and what's the probability of it being within a particular class. So that's the organizing we do. That's the only difference. The mathematics, as you're going to see, we've already done the math. We've counted, we've divided by the total, we've gotten the relative, which is a percentage, and now we have a way to measure probability, and then the rest is all about language. And again, as we saw with statistics, there's the definitions and the language behind. Sometimes that's the hardest part of it, is understanding the way they say it. And we're going to see this is even harder because the difference with they say and or, those two words, we do things a little different the way we count. So we're going to spend the next few days looking at, we know how to count, we know how to divide, but now we need to know what to count. And that's in the language and of what they're doing. We also did, this is still from chapter 2, we talked about, anyway, making a histogram. We talked that we would let our technology do most of it, which we still will. But when we see a histogram, if it's a relative histogram, over here are our percentages, which will allow us to do probabilities. We're able to look at this particular bar here. So the number's 262.5 to 298.5. And we could say that there is a 20% chance, if we randomly selected a number out of there, that our number would be within that class, 20%. So we now have a chart that's giving us percentages for these bars. We also started talking about percentage of data with the empirical rule. Remember, we had this, and this was on the exam, the last question, I think it was. We have a frequency histogram that's, and again, a lot of stuff, it looked like this. Does anyone remember what was the probability from 1 standard deviation below to 1 standard deviation above? Here's the mean right here in the middle. What percent was in there? I heard the 68. Yes, good. 34 on both sides, 34 below, 34 above. So it would give us 68%. Okay, so we'll start looking at that. So when you get a histogram and you get a lot more data, that's what we're going to move towards. We get something that's continuous, and we get those percentages. But just think those percentages that were on these distributions, they come directly from building histograms. Okay, and so then we're getting percentages, and these are, we're going to treat, this is where statistics and probability get married. They match up. Okay, so that's why we're doing probability. So that's different. I thought we were doing statistics. Statistics has as its underlying base probability, the chance of something happening. So we collect data. That's what we talked about so far in chapters 1 through 3. Now we're getting the mathematical theory about probability, which again, we've done the math on it, but now we're going to look at what probability means, and then we'll connect it to data. Getting data, probability together, we're able to make more accurate predictions of what might happen in the future. We don't have a 100% we don't know for sure, but we have a better chance. Okay, so let's get into the probability theory. If I have 100%, then it's certain. I know what's going to happen. So occasionally you'll look at your weather app, it says 100% chance of rain. You look out the window, it's probably raining, right? That's usually the only time it gets to 100%. If it's not raining yet, it's usually maybe 99. There's a really good chance you could see the storm coming. You see it coming. But if it's raining, it's certain it is raining. It's 100%. There's other times where you might see a 0% chance of rain because there's not a cloud in the sky. Although, with mountains and stuff, you might not see them now, but by afternoon, we might have some rain. But so 0% would be something that isn't going to happen, can't happen, and is impossible to happen. Example would be like if I roll a die, 6-sided die, what would be the probability of getting a 9 on a 6-sided die? Can you get a 9? No, unless you have 2 dice. But no, with 1 dice, no, you can get a 1 through 6, but you can't get a 9. It's impossible. So that's the idea. Some probabilities are impossible because they just can't happen. Some are 100%. Some are really small, like winning the lottery. There's one for $1.8 billion. I don't know if you were following that. I I bought a ticket. I had some good dreams that night. Didn't win. Actually, I won $4, but because I matched the Powerball, but I didn't match the other ones. Um, Actually, I went on a group thing, so I won 1/10 of $4. Not a lot, but anyway, good dreams. That's about all I got out of it. I thought about what would it be like to have $50 million, right? Oh, what could I do with that? I could do a lot of good. I could relax. Well, now I'm back to work and I don't have the 50 million. So, uh, but there was a possibility of it happening. And somebody, I think it was in Texas, and there was another state they mentioned, Illinois or something. There's two people who actually matched and won. Okay. Very small probability for any particular person to win, but when enough tickets get bought, the probability of someone winning goes up. And again, there was if you followed along, there was like months nobody was winning the big jackpot. Finally, enough people bought tickets, and as it gets bigger and bigger, that's what happens. Somebody won, but even that whoever did win still had a very small probability of winning. 0.0000 something, a lot of zeros. You would say that's a zero probability. No, it's just a little bit above zero. It can happen. Okay, and usually nothing is completely 100% certain. You may have bought your ticket to go see your grandma over Thanksgiving break, and you're planning, and everything's going to happen, but things happen, right? You get sick or something, you can't go. So there's even if no matter how much you plan, you can maybe get to that 99%. I'm so certain it's going to happen, but something could get in the way. Okay. But this is how we start to judge it, right? Flipping a coin, we say is 50-50 because it could be heads or tails. So that's right in the middle. We don't know, there's not favorable or unfavorable. Closer we get to 100%, the more favorable something is to happen. It still could not, right? The closer to zero, the less favorable it is to happen. Okay. But in the end, our probabilities go from either 0 to 100% or from 0 to 1 as a number. So you want to look at 1 as 100%, okay, and the decimals are anything in between. That's one of the reasons I like percentages. It's easier to know we're talking about probability. We use the number 1 for other things and decimals for other things. So, but just remember, in the terms of probability, 1 is the same thing as 100%. Okay. A little bit of vocabulary. In studying probability, we do things called probability experiments. That means we sit around and roll dice. We draw colored marbles out of bags. We take a deck of cards and choose cards and those kind of things. And we're looking for what the outcomes would be. So probability experiment is actually going through the process of the random process of picking and see what comes up. Okay, and that's how probability theory was. And again, it is a theory, it's not a science, because you could have other belief systems thinking that the physical world just, is going to happen when it happens. There's some people believe in other things that influence the world, and that's okay. Maybe it does, right? There are outcomes in every probability experiment, and what those outcomes are is what could happen on a single trial. So if I'm rolling a die is a single, I could get a 1, 2, 3, 4, 5, or 6. So those are the possible outcomes. That's what could happen. And when I roll it, if it comes up 3, that's the outcome, right? I got a 3, outcome of that experiment. Sample space are all the possible things that could happen. So with a die, it would be 1, 2, 3, 4, 5, 6 are the possible outcomes. It's all of them. So the sample space always has to have 100% chance of happening. Something's going to happen. If we're less than 100%, we're forgetting to count something. Sometimes it's that nothing happens, right? Maybe you're flipping a coin, and if it lands on the floor, it doesn't count because it's got to land on the table or in the box or something. So there's that possibility that we don't get a result, but even that has to be accounted for in the percentages in the sample space. Okay, so the sample space has to include everything that could happen. And then the event is the particular outcome that we're sort of looking for. So oftentimes we'll say the event is I want to roll a 3. And if I roll a 3, I get $1 million. Okay, great. Okay, so I roll that. If that event doesn't happen, I don't get my $1 million. So the event is a particular outcome that we're looking for. However, it could be more than one thing. It could be, well, if you roll a 3 or a 4. So there could be more than one outcome in an event. So we'll look at the event is just saying, this is what we're looking to have happen. What is the probability of that happening? And we go from there. So for now, that's most of the vocabulary we have to look at. Okay, so now I want to kind of switch gears a little bit and talk about counting, because in probability, remember the first thing we really have to do is we have to count. And basically we count how many things are in the event, the thing we're looking for, divided by how many things are in the sample space, everything. And that becomes a relative frequency, which is a probability, right? So that's how we do it. So how do we count? Well, if we break things into groups, like we're getting dressed in the morning, and I find I've got 2 pairs of jeans, and I've got 3 different t-shirts, and 2 pairs of sneakers, red and black, how many different outfits could I put on that day? We can see the 2 is represented here by the jeans, and then we've got 3 shirts. But if you look at that, because we've got the 2 jeans and that breaks up into 3 shirts, that gives us 6 different outfits so far. And then when we add the shoes, either black or red shoes, that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what ends up working is you do this enough times, you can see all you have to do is take the 2 jeans times the 3 t-shirts times the 2 pairs of sneakers. And that tells you you would have 12 potential outcomes, right? Your sample space has 12 different possibilities. It's okay with this one, but just think about it. What if I had a closet full of 10 pairs of jeans and 20 shirts and 50 shoes? I don't know, not that many shoes, but the numbers could get pretty big, and I wouldn't want to make a tree diagram out of that particular one. I would just want to use the theory. Let me just multiply those things together and see how much I got. Okay, so that's what we're going to do a number of times. Is we're going to use this multiplication rule. They call it the fundamental counting principle. My professor, when I was taking probability, which was my major in mathematics when I was working on a master's. I didn't finish it, but I just went to math ed. But he called it the multiplication principle, which is what it is. Counting principle, you're thinking of counting, but multiplication is just a faster way to count. Okay, let's think of it that way. Another example, and we can always use that tree diagram, but for those of you in the medical field, we've got 4 different blood types, and then each blood type has a positive or a negative that's associated with it. And so we could come up with all the sample space for blood types. Okay, then you might need to know how one blood type interacts with another and which ones can receive the donors, that kind of stuff. But this, at least using a tree diagram, can help us get all the different options when there's not that many. We're going to see that we could quickly run out of space. So then the other thing we're going to talk about are simple events versus non-simple events. So on the right side here is a tree diagram of a probability experiment where we're going to flip a coin and then roll a die. So the outcomes, the first one, you get either a heads or tail. You got a heads, then when you roll the die, we mark that as H1, H2, H3, and so forth, which means you got a head first, and then you got this number. If you got the tails, then that is designated by tails 1, tails 2, tails 3, and so forth. So as you can see, the tree diagram says there are 2 times 6, 12 different outcomes, right? The sample space is listed there. So a simple event simply means that there's only one outcome in the event. So something like tossing a heads and then rolling a 3. tossing a heads, rolling a 3. There is only one outcome that ends up being a heads and a 3. Okay, so that's a simple event. What does a non-simple event look like? Well, it has more than one outcome. It's not a simple event. And an example of that would be tossing a heads and then rolling an even number. And so you get the heads, and then there's H2, that would be rolling an even number, H4, and H6. Okay, so 3 different outcomes possible to fill in that event. So it's a non-simple event. Okay, you have to count carefully. So simple events are easier to deal with because there's only going to be one outcome. And so when we calculate the probability up here, it's simply there's one way of getting a heads out of with a 3 out of a total of 12. So 1/12 is our probability. Below, since it's not simple, we had to count them, and we thought, oh, there's 3 different ways to do that out of 12, which is reduces to 1/4, which is 25%. Okay, so we can still calculate the probabilities with both, but notice with a simple event, it's only one way of happening. So that's the easiest way. Fundamental counting principle, this is just a formal way of saying when you got things in groups, or you do something first and then something second, that's the 2 groups, to get the total, you multiply. That's really all it's saying. So I just call it the multiplication principle. If you remember it that way, multiplication principle. Well, what do? We multiply. It's easy. Fundamental counting principle, then what do I have to count? No, we have to multiply. So just call it the multiplication principle. And we're going to apply it a couple times, and we'll see how this works. We can do a lot of things. So we're purchasing a new car. Notice there's a couple different options. There's 3 options for the manufacturer on this particular car lot. They have 2 sizes for each of those. And then there's 4 different colors for each of them. And so what we could say is there are at least 3 times 2 times 4, 6 times 4. There's 24 different cars that we could walk away with, right? That we could buy on there. You could do the tree diagram, which is in the next slide. So yeah, 24 ways, just multiply it. Tree diagram gets a little bit messy. I would have problems writing this out by hand. I'm just a little sloppy, but you can see there's 24. It's getting to the limit of what we could probably do with a tree diagram. Now, you notice that the nice thing with the multiplication principle is multiplication is commutative. You could do it in any order. So you could actually switch the order of the tree diagrams. You could start with the colors and then do the brands and then the size or some other option. It doesn't matter. You'll still end up with 24 at the end, 24 different options. But tree diagrams sometimes are helpful, but only if it's smaller amounts. Okay. So now let's start using this. We'll sort of start using this how we count for like probability. So we've got a car security system that has 4 digits. And we do this a lot, like how many license plates could we have? How many phone numbers could we have in given a certain thing? So if we have the digits 0 through 9, how many symbols is that? 0 through 9. Yes. Good, 10. A lot of people think 9 because they think 0 through 9 is 9. No, you got to count them with your fingers. You'll get that's with that 0 in there, that gets you the 10. So there's 10 in there. What we're going to do is do it 3 different ways. How many access codes are possible? First, when each digit can be only used once. We'll see how we do that. Each digit can be repeated. And then there's a special rule that 0, 1 can't be used for the first digit, but then you can repeat. So we'll just see the way I go about calculating these is I set up, since we're going to have 4 digits, just underline 4 spaces. We're going to do it. And then what we're going to do is think each space, how many choices do I have for that space? So for number 1, since each digit can only be can be used only once. For the first digit, how many choices do I have for putting something there? 0 through 9. I could use any of those numbers. So that gives me 10, right? Okay. So I have 10 choices for the first digit. I'll put a 10 there. And then I always like to just do this. We're going to multiply because it's the multiplication principle. So for the second digit, since I can't repeat whatever I put there, it doesn't matter what I put, but I used up one. So now how many choices do I have? 9. And then I use up one of those 9, and so I only have 8. And I use up one of those, I can't repeat it, so then I've only got 7. This is something called, it's on getting close to being a factorial. So when you multiply numbers in order all the way down, that's called factorial. You may be familiar with that. We'll look at, it's built into the calculator. But this gives us, if you take 10 times 9 times 8 times 7, you get 5,040 options. And no, I didn't use some special method to just calculate that. I just did it earlier, remembered it. And I do this example enough that I remember that 10 times 9 times 7, 8 times 7 is 5,040. Okay. But that's, you'll be able to do all of these with this multiplication principle. You're just thinking each one, how many goes there. For the second one, since each digit can be repeated, right? So it's sort of the same thing. So I've got 10 for the first, but since I can reuse whatever I used, I still have 10 for the second, right? And since I can reuse it, I still have 10 here, and I have 10 here. Notice we're not having to memorize any special formulas. It's just I'm thinking for each number, each slot, as a different thing. How many different choices do I have? And I have to apply the rule that they're giving me. I multiply these all together, and notice that gives us when you multiply by 10, you just count the number of zeros. So that is 10,000. 1, 2, 3, 4. One with 10 zeros behind it. So notice almost double the amount of options if we can repeat. Okay. Now, you might think a code like 1111 is not as secure, but it is another option that wasn't available to us on the first one. So there's more different options. So the probability of someone breaking into your car is less likely if there's 10,000 codes than if there's 5,000. Take them longer to guess them all, right? Probably 5,000 is enough anyway. But let's see the last one, how we would do that. Again, we just follow the rules. The first digit cannot be a 0 or 1. So how many choices do we have for that first digit? 8. Good. Yeah. Can't use 0 or 1, but we got 8 other choices. But now it says we can start repeating, and we can use 0 and 1 for the second digit. So how many choices do we have for the second one? 10. Since we can repeat, we have 10, and we have 10. And again, multiplication principle, just multiply those things together. And in this case, we get 8,000 different codes. Okay, 2,000 less than without, by taking out the 0 and 1, we lose 2,000. But again, that happens like with phone numbers, right? You can't start a phone number with 0, because if you do, that goes, the 0 is reserved for going to the operator. 1 is typically reserved for going to long distance or out of your area code. So that's why, like phone numbers, you can't use 0 or 1 for that first digit. Okay. So far, making sense? Again, just thinking, we're going to, and we'll do this a lot because it's like, how many license plates are possible? Well, we got to count letters and numbers, and it's all dependent upon there. Okay. In the end, we get a probability by counting the number of outcomes in an event, and we divide it by the number of outcomes in the sample space. Okay. So what we were just doing on the previous slide on those codes is we were calculating the size of the sample space. What are all the possible codes? And now maybe I've got 3 cars, so I've got 3 different codes or something. We can start doing some probabilities. Then we got to define what that event looks like. A lot of times in probability, like, your card code is going to be one number. So 1 divided by that gives you your probability, right? So let's just see, a lot of things make an assumption that things are equally likely. Not all things are, but some are. So if we're rolling a 6-sided die, um, the event is rolling a 3. How would we calculate that? How many 3s are on a 6-sided die? Just one. And since it's a 6-sided die, there's 6 other options. 1 out of 6. That's our probability. And you could turn it to a decimal. I think it's 0.16666, and which is about 16.7%. Did I get that right? I think sometimes I remember random things. What's the probability of rolling a 7 on a 6-sided die? How many 7s are on a 6-sided die? 0 out of 6. That's an easy calculation. That's 0%. Okay. You can't roll a 7 because there is no 7. Okay. That's where impossible comes. Rolling a number less than 5. That'd be 1, 2, 3, or 4. Not 5 because it has to be less than 5. So we've got 4 out of 6. And again, so probability is just counting and then dividing. Counting twice, right? Counting the event, counting the sample space, and then doing that division. That's all there is to it. So mathematically, fairly simple. There are formulas that come up later on, but if you keep this in mind of just counting the way we've done with the multiplication rule, we'll be able to solve most issues. Okay, so we look at our sample space, it's all out of 6. That was talking about theoretical probability, so it's just things are equally likely with the die, which is usually happens, right? But because people can make money playing these games at a casino, what do people do to a die to make it so it's not a fair die? They might weight it so it's more likely to roll a particular number. Okay, so that's where empirical probability comes in, is we make observations. So we just don't assume that when we roll a 6-sided die that each one is equally likely. We actually do it. We actually roll it and test it out. And so then we're recording frequencies of the event. How many times do we get a 3, per se, divided by how many times we rolled. And then that becomes the probability. And again, if it's not 16%, 1/6, we're going to say maybe there's something with this die. Maybe it's weighted. Maybe we examine it some more. Maybe it's so old it's rounded the corners or something. But empirical just means to actually do the work, count. This is primarily used in sports statistics, right? Batting average, how many times did the person come up to bat? And that's going to be their sample space. How many times did they get a hit? That goes in the numerator. So that divided by how many times they went to bat, that's your batting average. It's a probability, 34% chance of getting a hit because of past things. Basketball, free throws. What percent of free throws does a person make? Well, they count how many they made or attempted, and then how many they made. So the number made divided by the number attempted might put you at a 70%. So you're a 70% free thrower, maybe on a regular day, but you could have a good day or a bad day. So maybe you do a little bit better on some days and a little bit worse on others, but that's empirical probability. Okay, so we're actually going to count. We do this a lot in statistics. Most things is because we go out and take a survey to see what's happening. So here's an example. They did a survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So they sampled 1,502 adults. They give a pie chart with the results, and some read no books, some read both print and digital books. Some adults only read digital books, and some only read print books. So then the question is, what is the probability that the next adult surveyed read only print books during the last year? So again, we're going into our statistics, into our data, and we said, well, in our last survey, 560 people read only print books out of a total of 502 or 1,502. So if we simply divide those two, that will give us a percentage or a decimal, which we will turn to a percentage, and that will tell us our probability. You could also add all the slices together, but they told us earlier on that it was 1,502, so that's what I would do. When you divide the only read print books by the 1,502, we get 37.3%. Again, could write it as a decimal, but it's the same thing as 37.3%. I just think the percentages look prettier. And so I got that feeling. It's close to 40%, so there's a 40%, 40 out of 60. It's not a 50-50 chance, but it's not a 0% chance either. So it's like, 40% chance. So it's just a way of measuring that if our next person that we're going to survey is randomly chosen, that's about, if it's consistent with the past. So there's a lot of ifs in here, right? Then they're likely to be a person who reads only print books. 40% chance. What would be the chance of that they're not an only print book reader? 40% chance that they do. What would be the percent chance that they don't? Let me change the question. If there's a 40% chance of rain, what's the chance that it doesn't rain? See, that's faster. So remember, this is what we call the complement. We'll look at a slide there, but the probability of something happening and the probability of it not happening always have to add 100%. That's because they're complements. It either happens or it doesn't. There's not a halfway thing. Well, it sort of happened, but no, it either happens or it doesn't. That's the way we've set up these events. So it's got about a 40% chance of happening. It's going to have a 60% chance of not happening. And what we'll see is, like for this exact one, we could simply take 100% minus the 37.3, and this would give us the probability of not happening. You could also go and add all the other ones, and because those are, if this doesn't happen, that means they're in one of the other groups. But you're going to see this is the easier way to do the calculation. Okay. We can use frequency diagrams or frequency charts, frequency tables, whatever they call them. And so here's one. And again, I'll just kind of go over there. We're told that there are 3,000 users from this survey, and we see that down here. The total of the frequencies is 3,000. So it's nice when they give it to us, we don't have to go through and add these numbers together. And we're asked, what is the probability that the next user surveyed is between 25 to 34? We look at that. Well, there were 765 in the past survey. So if we do 765 divided by 3,000, we'll get our probability. I'm thinking that's, let's see, well, let's just do it. 765 divided by 3,000 is 25.5%. Actually, it's 0.255, but if you also multiply it by 100, that turns it into a percentage, so 25.5%. It's about a 1/4, 1 in 4 chance. And you look at the numbers, yeah, it's one of the higher numbers, isn't it? So it's actually the most likely. Everything is less than 25% chance. But that's how we're going to calculate probabilities. What's the event? How many's in that event? Divided by the total sample space, how many's in there? Just a real, that's all probability is. In fact, that's why I chose it as my math major. I thought, all you have to do is count and divide. I could do that. It gets a little more complicated, but not too much, we go there. Here's the deal, though, is there's this thing called the law of large numbers. What it simply says, it's not this, that the numbers themselves are large, but you do many, many trials. So if you're flipping a coin, think about it. If you flipped it 3 times, would it be possible to get 3 heads right in a row? Sure it is. Yeah, you could do it. Sometimes people are flipping coins to make their decisions, and well, okay, 3 in a row. Hey, it's all heads. It must be, ordained that way, right? But that's probably. How about 10 times in a row? Is that possible? Possible, but less likely. That's what the law of large numbers is saying. 100 times, while it's possible to get 100 heads in a row, it's less likely. The more trials you do, the more likely you're going to get that you've got 50% heads and 50% tails. Okay, but in the beginning, if you just a few, it could be all over the place. You could get all heads, you could get all tails. There's a lot of different options that could happen. Okay, but the law of large numbers says that in the long run, the probabilities will come out. So I throw this out because there's casinos around all over the place. Casinos are basically temples of probability. Everything is by chance. Some people win, some people lose. But who do you think always wins? The casino. That's why they're so big and beautiful, and they got all these things they give away. And so it's telling us that the probabilities are set up that in the long run, the casino's going to win. So if you go in and you win something, especially if it's a big jackpot or something, what's the first thing you should do? Leave, right? Yeah, because otherwise what happens is you say, oh, it's my lucky day. I'm going to keep playing. I've done this before, and then your big jackpot goes away and you give it all back because the probabilities will, the math will tell you it still favors that casino. Now, some people win, and they need people to win, because if nobody won, people would stop going and they wouldn't have their money. So they need people to win. They need people to win big, but only a few of them. They need other people not to lose big, but just to lose enough that they want to keep coming back to say, let me win back the money I lost last week, right? So that's the idea. But just remember, law of large numbers, it's always in the favor of the casino. So the longer you play, the more the odds are against you, because that's how it's structured. Now, if you can find a game that's got the probabilities in your favor, then yes, you want to play those as much as you can. Okay, so another type of probability, and then we're almost done with this section, and we'll take a little break. Is subjective probability. So we've talked about theoretical, which is just a dice has 6 sides, so there's 6 possibilities. We assume they're equally likely, so a 1 in 6 chance of getting a 3. That's theoretical. Empirical, observation, we actually roll the die 100 million times and figure out what happened. And then subjective probability, we don't do anything, we just say, hey, I think I got 90% chance of getting the job I just applied for because I feel good about it. Or I got a 10% chance because I did the interview and I don't feel so good. And I've done both, and actually I got this job. I didn't feel so good about the interview, but they hired me anyway, so I guess I did okay. Sometimes you just never know. I had ones that I thought I did real good. I didn't get the job offered, so somebody else did better, or they liked somebody. So, but that's subjective probabilities, right? We do it all the time. We do it all the time. We're just kind of, part of it is we're also maybe running that calculation. We're at the coffee shop waiting for our friend. We think back, maybe our friend, maybe they're usually late, maybe they're not late. We think about that, right? Whether we're going to stay there and keep waiting another 5 or 10 minutes, see if they show up. One friend, oh, he always flakes out on me. I give up. I'm just going home. The other friend, he's usually there. Maybe he got caught in traffic. I'll wait another 5 minutes. So subjective probabilities. We're thinking, what's the chance of it? Okay. Doctors sometimes using subjective probability because they don't really know. This is just a formalized thing of the rain, no rain, right? 30% chance of rain. So, whatever it is, we'll say if there's a 30% chance of rain, there has to be a 70% chance of no rain. So those always have to add to 100. And that's what, which one is it? This one is saying that they would add to 1. Again, it's a little confusing when we think of 1. I like to think of this as 100%. Okay. Also, if you take 100% minus one of those, either the rain or not rain, you will get the probability of the other thing happening. So again, this will help you when you have the questions that what's the probability of something not happening. This is going to usually be an easier calculation than calculating all the possible ways that it could not happen. And let's take a look at an example. I think this is the next one. So we did this earlier, except they added one little word. And this is what I mean about probability and statistics. This little word of a not has changed this completely. Remember when we did it before, who is in the 25 to 34%, we just simply took this number divided by 3,000. And we were done. But with the not, it means we have to actually, if we were to do it in the, just follow the directions, we would calculate the probabilities for everything else, and then we would have it. But I'll tell you what, that takes more time, right? The easier way to do is say, okay, let me calculate the probability of this happening, and then I can subtract it from 1, or 100%. A good way of writing 1 mathematically when we have a fraction is to rewrite it as 3,000 divided by 3,000. That's 1, right? Because when we're subtracting fractions, we need to have common denominators. This is where we bring back our math, all the math stuff we've learned over the years. So 3,000 minus 765 gives us 2,295. Did I get that right? Let's see, 6, wait, oh, 6 from 9, 35. I believe, out of 3,000. Also, you could say, well, 765 over 360 was, we also calculated that. That was 25.5. So we could percent. So you could subtract that from 100, and you'll find that you'll get 74.5% probability of it not happening. Probability it's not 25 to 34. Okay, so notice how that calculation was easier than calculating each of the other percentages and then adding them. But I remember when I was taking classes in this, I was on an exam. I spent like 15 minutes, and I got to, oh, dang, I could have done this in 2 minutes or 1 minute if I just subtracted from 1, because I was calculating the ways of all the ways it couldn't have happened. Just didn't. And that's why I emphasize that, because when I did that once, afterwards, I always check, is the not, okay, I'm just subtracting from 1, much easier. In fact, there are some examples we could give you where there's not enough information to calculate all the other ways, but calculating how it could happen and then subtracting from 1, that's possible. Okay, it's easy. So remember that. We're gonna, yeah, we'll do the first part. The second part I'm going just to highlight, and then we're going to talk about it in the second half. So here's event A is tossing a tail. So we're flipping a coin and then spinning an odd number on this spinner. So the way we do that calculation for the first one, and I'm going to highlight this word and. So first of all, we know there's 2 things that are going to happen, and they're both simple outcomes. So, well, no, the second one's not simple. First one, get a tail. So you flip a coin, you get either heads or tails, right? So what's the probability of getting a tail? You flip a coin. Is that 50%, 1/2? I'm going to do it as a fraction, because what we're going to do is we're going to end up multiplying, but you could do it as a percent or a decimal. So that's the first thing. Remember, there's going to be a second thing that happens, and we're going to use that multiplication principle. So some of these things, that's how we do that. What's the probability of spinning an odd number? Well, we look down at our spinner. There are 8 slots, and we're told that they're each equally likely. so that we could get 8 different slots. How many of those numbers are odd numbers? There's a 1 and a 5, 7 and a 3, looks like 4. 4 of the numbers are odd numbers. And so we would say the probability of event A happening, 1 times 4 is 4, 2 times 8 is 16, which reduces down to 1/4, which is 25%. Okay. What I'm going to highlight for event B is that tossing a head or spinning a number greater than 3. Now the or changes it. It's not and doing it, it's or doing it. So either one, if I toss a head, I'm done. I've achieved that event. If I don't toss a head, but I spin a number greater than 3, that also counts. If I do both, that also counts. So when we look at or probabilities, there's some complications because there's multiple things, and I got all these balls in the air. We're going to talk about it in the next segment because what we need to do is understand whether this is what we call mutually exclusive or not mutually exclusive. And that will depend upon the calculations. The one thing we're going to do, though, is we're going to see that when we have or probabilities, what we're going to end up doing is adding, not multiplying. This is the one where we add probabilities. Notice up here with and, we multiplied. So pretty much everything we're going to multiply. But with or probabilities, it throws in a little wrench to this, and it's this or both. So what we're going to do is we're going to push it off a little bit because the next presentation takes a deep dive into the or probabilities. And I was doing this in class yesterday, and I went right over the word or and started doing it as if it was an and. So I'm going to have to go back to that class and say, wait, you got to read carefully. This is the type of things. And or, you're worrying about the whole big picture, but you got to look at these little things. And ors are 2 different types of calculations. Okay, so we're going to freeze it here. There's a couple more steps in here, but what we'll do is I think I'll take a 5-minute break, and then we'll come back and introduce mutually exclusive. It's a smaller set, and then probably about 20 minutes on that, and then I'll get you your exams back, and then we can work through those.